we look at equations of motion. All of our equations of motion have, there's one thing that we have to remember, it's constant acceleration. These equations don't work for variable acceleration. And we have three equations. The first one is quite a simple one. V is the final velocity. U is the initial velocity. A is the acceleration. And T is time. To use these equations of motion, we have to use SI units. Okay, they won't work otherwise, which means that our velocity is in meters per second. And as we know from last week, acceleration is meters per second squared, and it's really easy to write a 1 there instead of 2 because I did it myself a number of times. And it's probably no surprise then that time is seconds. Remember, we also need direction. For our vector quantities, which are velocity and acceleration, but time is a scalar quantity, and so we only need the magnitude, not direction. Our second equation brings in another variable, and that is displacement. And it is measured in meters, and it also has a direction. And so that tells me that for my equations, if I have direction, that means positive or negative sign. That's how I'm going to be using it in my calculations. That's how I'm going to calculate, make sure I've got my direction correct. And we have one last equation. But it's just, I guess, a combination of the different variables. So we've got displacement in those two, we've got time in these two, and this allows us to do our calculations. We've got some following the steps in the booklet which are good steps as far as how to go about solving questions involving equations of motion. And that the first step is to write down all the information that you have. So we're going to have it as a list. We need to remember the sign depending on the direction of the motion. We must have the variables in SI units, so we might have to do some conversions. And then make sure that our answer is also correct. If it's a vector, it's going to need direction. Now, for a lot of our questions, if it's horizontal motion, so it could be like a car, in which case, you might have acceleration is 6 meters per second squared, something like that. Okay? That sort of sounds reasonable, doesn't it? So you're going to need to be given a value for the acceleration if it's horizontal motion. Something that a lot of students find a little bit tricky is vertical motion, because acceleration is never going to be given. So we have a constant. We have the gravitational constant, G, that operates for up and down motion. And the convention is that up is positive. So that means down is negative. And our acceleration then due to gravity is always downwards. So our acceleration is equal to negative, oh hang on, sorry, on your formula sheets. Your formula sheets has it as 9.81, so I have to use the same one. Okay, so this is a given for any up and down motion. The question won't tell you that. Another thing that students sometimes forget is if we're throwing an object up in the, like a ball, something like that. We did talk about our graphing before, and you know, if this was a displacement time, we give it an initial velocity. Okay, we throw the ball up in the air, but at the top of its trajectory, its velocity is 0 at the top there. Yeah? Okay? And so for an up and down motion, we not only know acceleration, we also can work out our questions to make sure that we're looking at the first half or the second half of an object's motion so that we know the final velocity. That allows us to use the equations. And the other thing to know about our up and down motion is it's symmetrical. And so the time taken is equal on either side. Okay, so if I call this one like T1 and this is T2, T1 equals T2. If we're landing back at the same height, okay, we have to be back to the ground. But that's another thing that helps us work out what's going on for our motion of our objects. All right, so if we drop something or if we throw something in the air, it's always acting with acceleration due to gravity the whole time. And in fact, we'll look later on and say, well, there's the weight force acting on everything all the time anyway, in close proximity to the Earth. And so this is only prevented from falling on the ground by the table being there. We will look a little bit at air resistance, but we generally ignore air resistance. So unless a question tells you to consider air resistance, you're going to ignore it. And it's reasonable to ignore it because at low velocities and over short distances, it is negligible. It's so small it really doesn't make much difference. But if you've got higher velocities and travelling over longer time, then it can start to have an impact. Now, the mass also doesn't matter. You notice that there's no mass in here. So objects fall the same way, no matter what their mass. And that is quite a difficult thing to get your head around. But the only thing that impacts on the way objects fall is their shape because of their resistance. All right, so here we have an example on page 30. A coin is thrown upwards. Its acceleration due to, oh, I don't know. No, that's not really a wet example. Let's have a look at the worked example on page 31. What is it? An acceleration of a car that has an initial velocity 5 meters per second north. And what we're going to do then is how you need to set yours out. Initial velocity. The moment you read that, you write it down. It speeds up to 15 meters a second north. So that's got to be its final velocity. And it did that over 2 seconds. Oops, 2.5 seconds. I know that the second number is a velocity because of the units as well. Now, sometimes there are errors in the booklet, as we know, but in general, we can look at that and say, yes, I can match up my units as well to help me if I'm getting confused with the way the question is worded. Now, I look to see, what am I asked to find? Finding the acceleration. Once I've written down all the information from the question, now I look at my equations. Which one has got all the information that matches my problem? And it's obviously this first one here. And because I'm finding time, I can transpose my equation first, if you like.
Finding acceleration, aren't you?
Oh, you're right there. Yeah, well, that's almost the same. Thank you. And then we can substitute in. And we get here 4 meters per second squared north. And I'm going to double check and look at that and think, is my direction correct? Well, I was speeding up, so I think that makes sense that my acceleration is positive. Okay, but it's a good idea to always go back and make sure that that works out well in the context of your question. If you've got your velocities around the wrong way. So the second example here is a ball is thrown vertically upwards from the ground. It takes 1.5 seconds to reach maximum height. So I don't know its initial velocity, but I do know that its acceleration is due to gravity. And I do know that at time 1.5 seconds, its final velocity then is 0. Okay, I can work all of that out. I don't have to have these values given to me. I can just infer them from the up and down motion. So yes, we say up is positive. So we want to find the initial velocity. Now when I look at these, it's the same equation that I'm going to be using. So v equals u plus at, or u equals v minus at. So u is equal to 0 minus negative 1.81 times 1.5. Okay, so that's why it's important to have the signs correct. And we'll get 14.7 meters per second up is our direction. Okay, remember we're setting up as our positive direction and down as the negative direction. Right, our third example, which is on page 32. A ball falls off a 15-metre balcony. Sometimes a diagram can help too. So we have a ball here, and it's going to fall off the balcony. What velocity does it strike the ground with? Well, its initial velocity in this case, it's dropped. or falls. Okay, it's not thrown down. So its initial velocity is 0. It's falling under gravity, and so its acceleration is going to be due to gravity. We don't know the time, but we do know that it fell 15 metres. So its displacement is 15 metres. But it's actually going down. It was at positive 15, but as it goes through this motion, it's going down towards the ground, so its displacement is going to be negative 15 metres. And we wanted to find its final velocity. Now I look at my variables and I can see that it matches up with the third equation. It's that one, v squared equals u squared plus 2as. I don't need to do any rearranging. V squared is equal to 0 squared plus 2 times minus 9.81 times, in actual fact, these get lost with the squaring, don't they? Our sample answers have just given us the answer. If I find the answer from square rooting, there are two possible answers, aren't there? The positive and the negative one. So now I have to look at that and think, well, which one makes sense? It's moving down towards the ground, so it's going to have to be a negative velocity. Oops. So it's either negative 17.2 meters per second, or I could say 17.2 meters per second downwards. Does that make sense? That you need to write down information from the question and then find the appropriate equation.
Will we be marked out if we just leave it as well as 17.2?
That is a good question, and it depends on who marks, and so it is a possibility. Big debates happen over marking. You could potentially lose a half a mark, because, but really, by rights, that should be okay. That should be fine. Okay, let's move on then to work